Good afternoon, everyone. I am Susanna. I'm a third-year PhD student, and my research involves the development of an ASIC implementing a neural network for position sensitivity of gamma rays in radiation detectors, such as those used for medical imaging. So in the field of medical imaging, there is an increasing need of improve image quality to perform better diagnosis with reduced scan time and injected dose. And the total body PET scanner, thanks to the extended field of view, can provide superior sensitivity, but at the cost of an increase in number of channels that leads to a huge amount of data that has to be transferred, digitized, and processed, which is the main bottleneck of conventional digital system. So what we propose to streamline this process is an ASIC implementing a neural network for the in-sensor signal processing. And neural networks are demonstrating superior performances in localizing the gamma rays emitted from the patient body for image reconstruction purposes as an alternative to conventional reconstruction algorithms. So what we propose is to integrate the neural network ASIC inside the PET detection module in order to perform the in situ localization of gamma photon interaction. The neural network is implemented analogically as a crossbar array of programmable switched capacitors, where the variable capacitor, represents the synaptic weight. The ASIC can perform analog operations directly on analog signals that comes from the photosensors, so without the need to digitize all channels, but only the two final outputs that are the X and Y predicted coordinates will be then transmitted and digitized. This approach has the advantage to reduce the power consumption and latency, and therefore improve the overall energy efficiency of the system. So the operation of the inference, which are the multiply and accumulate operations, are performed in a charge domain. So briefly, the input voltages sample a charge on the variable capacitor, which is implemented as a bank of binary scaled capacitor, which implement the neural network weight with the 5-bit resolution. And next, in a second phase, all the variable capacitors are connected to a charge integrator in order to perform the accumulation operation. The integrator also performs the activation function, which is a clipped ReLU, just by clipping its outputs between the two power supplies. So the ASIC is fabricated on a CMOS 0.35 process, and this is the laboratory setup developed to characterize it, comprising PCBs, a microcontroller for communication between the PC and the ASIC, and an oscilloscope to visualize the ASIC output. So the ASIC is intended only for inference, therefore the training must be performed offline. And the training and the test dataset were obtained with a gamma camera simulator, which provides the photosensor signals, which are the input of the neural network, and the position of interaction, which are the labels, the target of the neural network. The weights are quantized during the training with a quantization-aware training approach, and the metrics used to evaluate the positioning performances of the network are the reconstruction error and the full width at half maximum of the reconstructed position. For PET applications, the target spatial resolution is better than 1.5 millimeter. So in order to better match the network running on PC and its analog implementation, we developed an analytical model of the electrical neuron for an analog-aware training. The model includes the principal analog non-idealities that were fitted with experimental data, and it also includes a post-layout integrator characteristics that implements the activation function instead of using an ideal ReLU function. From here we can see how the optimized model is more accurate in predicting the real output of the electrical neuron, and therefore this model will be used for train the neural network. So here I report you some experimental measurement of the network running on the ASIC. In order to test its precision in predicting the coordinates, we performed 200 inference measurement of the same input and measured the standard deviation of the predicted coordinates in order to evaluate the effect of the electronic noise on its performances. And it resulted in a full spatial resolution of 0.15 millimeters, which is good considering the target resolution of 1.5 millimeter. And we can also conclude from this measurement that the effect of the electronic noise does not have an important impact on the ASIC precision performance. We also tested the accuracy of the neural network on a grid of points, and here what I want to highlight is that the ASIC reconstruction error improved a lot from 11 millimeter to 4.5 millimeter when the network is trained with an analog-aware model. So even if these values still not sufficient for the intended application, but however it's a promising result showing that the model was good to predict the actual electrical neural network. So to conclude, this was a first proof of concept prototype that performs Mac operation in analog domain and can reach an energy efficiency of 47 gigaoperation per joule. And a new version is now under development on a more scale technology, and which implements also a larger network in order to improve the performances. And also a revision of the neural structure is being developed in order to improve throughput and neural network efficiency. Thank you for listening.